it done with, apparently. S.
So actually, we were just having a class, so maximum people haven't joined it. That's why.
Okay. So should I wait for a little bit? Can I wait a little longer? Okay. All right. So give it a couple of minutes. Okay, good. Someone's recording it. And I always wanted to ask, but I forgot. I keep forgetting. Who is the CR for this class?
So we are apparently having 6 CRs, like 2 for each section.
2 for each section. Okay, that's fine. I request the CRs and split it among yourselves to keep a recording of the lectures and download it when it's available, and have a folder with all the videos, if that is okay with you. Can someone take charge of that?
Sir, we have a folder for the notes and all, but not for the videos.
Yeah, I'm asking for a folder on your laptop or someplace, which can later on be shared, because I'm not keeping any folders. I'm not downloading the videos that has been recorded of my lectures.
Sir, actually, the September ones are already deleted. Like we had a time of like 22 days to download it from Teams.
Can you guys? Yeah, I understand. Can you guys get someone who has already downloaded it and have it on their computer? Can you ask them to share it with you and keep a copy of that somewhere? Someplace that is accessible to everyone.
Abhishek, can we use the Google Drive for that? If I'm not like,
yeah,
can we use
yeah, sure. You can use the Google Drive, of course.
So we actually have a Google Drive in which we are like continuously uploading all the lectures, but not the recorded ones, just the notes.
Okay.
So Abhishek, can we use the Google Drive for the videos as well?
Abhishek?
Yeah, I just had a internet lag. Was anyone telling anything?
Yeah.
Yeah, actually, I was just saying that if we could use the Google Drive for the videos as well, like we can upload the lectures. We are uploading the notes over there. We can have the lectures.
Hello, sir. Are you speaking? I can't hear anything.
Oh, okay. I think. Hear me? You have selective hearing problem with Sangeeta. I don't know. Okay. Anyway, I was asking if you can upload the videos on the same Google Drive that you're uploading the files to. The notes to.
Okay. Yes, sir. Yeah, I will do it, sir.
Yeah, thank you. And for the ones that have been already deleted on my MS Teams, can you ask some of your classmates to share the video that they have already downloaded from the Teams? So you'll have a copy of that. Just to have a repository where we can access the videos later on.
Yes, sir. I'll try to find out if anyone has it, or like if no one did, so it won't be possible to retrieve it. But whatever is possible, sir, I will take them and put it in the drive.
Thank you. Because I keep forgetting to record the videos sometimes. I keep forgetting to download the videos most of the time. And I've been handling a lot of courses. Like at least I'm teaching 4 courses this semester, and one more has just been added. So I can't do any of that anymore. And I have 2 kids also. So yeah, I can't handle all of that. So if someone can take responsibility, that would be great. Yeah.
Okay, sir.
All right. Thank you. And yeah, of course, you can, Abhishek, you can delegate it to someone else. I mean, if you feel confident of someone else handling the job, then you can always delegate it.
Okay, sir.
Okay. Thank you. All right. We'll cut to chase and start the class. I don't remember where we left last time. Does anyone remember where we left last time, where we stopped? I remember teaching this part. Okay, did I teach the law of mass action idea? No? Does anyone Has anyone been keeping track of what's going on in the class per se, or are you guys just following the notes? Okay, I'm not getting any answer.
So the
notes. Oh, okay. So we're basically lost. Okay. Okay. I don't know. All right. So I remember handling this part. Do you guys remember me teaching this part, like solving these equations self-consistently? Does anyone remember? If you don't remember, let me know so we can go over it again at the expense of time. But that's okay. Does anyone? What's your opinion? Do you guys want me to go over this, or has this already been covered and you want to move on? Anyone? Anyone at all? Hell. You guys want me to take a call on it? Did someone say something? There are 144 students, maybe more, and no answers. Oh, wow. Okay, silence says a lot. Okay, all right. So let me start from the start, wherever, okay, PhD, the part 4 of my notes. I remember teaching this, but I can go over it and, maybe it'll sink a little deeper in your brains, maybe, I don't know. Okay, so we've been talking about semiconductors. Of course, you're going to be computer engineers, and you will be dealing with semiconductors for at least for the next decade or so. So you need to understand the physics of semiconductors. I'm not even sure if you're going to be using the physics per se in your jobs, but it's important to understand the principles behind the semiconductor devices. Okay. So we talked about. I think we talked about a little bit of quantum mechanics, how electrons behave in semiconductors, and what a valence band is and conduction band is. How do they come about, and why does the gap arise between the semiconductor, between the valence and the conduction band, and all that. Okay. Now, the question that I pose here is that how would you calculate how many free electrons are there in a semiconductor available for conduction, and free holes, of course. When I say electrons, I also mean holes. For now, we are thinking about intrinsic semiconductors, which means the number of holes is equal to number of electrons. Okay, so we should have a way of calculating the number of electrons. Okay, now a valence band and a conduction band. When I say the valence band and the conduction band, what I mean is that a lot of densely packed states. Okay, when I say a state can take 2 electrons. That's what I mean by a state. Okay, and a state is defined by its energy. Right, it has a specific energy, and you can only put 2 electrons into that state, which means that those 2 electrons will have that energy, right? And so you have a continuous distribution of a lot of states. Okay. And from the bottom up, if you keep increasing the energy, you will have a number of states available at each and every energy level. And right at EV, that's the maximum energy possible for the valence band, beyond which there won't be any states available. Okay, you will have no states from EV up to EC. There will be no energy levels. Okay, that's the band gap. What that means is that at those energies, you cannot pack in any electrons because there are no states available in the semiconductor. Okay, and beyond EC, you will again have states, right? Number of states stacked, and at each state you can pack an electron, 1 or 2 electrons, 2 electrons if you consider split. Okay. Now the question is, given a certain interval of energy, let's say dE, how many states are there? Okay, and that question leads you to the concept of density of states. I think I talked about that earlier. Density of state gives you the number of levels, number of states, number of possible states that you can have within a certain interval, energy interval. Okay, and that is one factor. The other factor is what is the probability of occupation of those states? That is given by Fermi Dirac distribution function. Okay, I talked about both of them. So there is a part of there's a idea of density of states where you get the number of states within a certain interval, and you also have to take into account whether these states are filled or empty. Okay, in general, at temperature T equals 0, the conduction bands of the intrinsic semiconductor would be filled or empty. Anyone? Anyone? Back up.
Empty, sir.
Empty, exactly. All right. So as you raise the temperature, of course, it doesn't mean when I say the conduction band would be empty, it doesn't mean that there are no available states. There will be available states all the time, right? And when you increase the temperature, what happens is available states are occupied by electrons. At T equals 0, these states are not occupied by electrons. So there are two factors that count when it comes to counting the number of conduction electrons. One is the availability of states in which the electrons can reside. Second is the probability that the electrons are actually residing in those states. Okay, those are the two factors. And the total number of electrons within a certain energy range equals to E is given by this equation. Okay, that's the electron concentration N, which is the product of the density of states, basically GC, that gives you the number of states available within an energy range E and E plus TE, times the probability of occupation of those states. Okay, F. Now, the curious thing is that the Fermi Dirac distribution function, if you remember, it has the EF in it. It has a parameter called the Fermi Energy. Okay, I think we talked about Fermi Energy. Fermi Energy is the maximum energy up to which you can the electrons are filled, and beyond which there are no electrons in a semiconductor at T equals 0. At temperature T equals 0, EF is the maximum energy that the electron can have. Okay. And this kind of tells you the cutoff where the states are occupied and beyond which the states are unoccupied. Okay, so you need to know EF. Okay? That's a parameter that goes into calculating the total number of electrons here. And as I said, GC is it's a density of states. Now, for the total number of electrons, you have to integrate over all the energies, of course. Okay. You're only counting the electrons within a given interval of energy. So for the total number of electrons, you have to integrate over all energies from EC up to infinity, right? So how is Fermi energy defined, by the way? Fermi energy is defined when you keep adding an electron to available states. And if you have, let's say, a certain number of electrons, if you have 100 electrons, if you keep adding those electrons to the available number of states, you fill up this the ground state, the bottommost state with 2 electrons. You go to the next available state. You fill that with 2 electrons. You go to the next available state, fill it with 2 electrons, and keep going on and on and on. And as you keep going higher and higher in energy, once you exhaust your 100 electrons, there is a state at which you fill the electrons above which the other states that are above the state that you just filled are completely empty. Okay, and that state, the energy of that state is Fermi energy, right? So Fermi energy is actually dictated by the number of electrons that you have in your hand, right? So the concentration of electrons, N of T, actually tells you what is your EF. Okay, but look at the equation here. The equation says that N of T is dictated by EF. Okay, you put in the EF, you calculate N of E of T, and then you integrate N of E of T, E comma T, and you get N of T. Okay, that's the electron concentration. So the mathematics tells you to go one way, whereas your intuition tells you to go the other way, right? If you want to calculate EF, you need to know the total number of electrons, and if you want to know that mathematics says that the total number of electrons is given if you have the EF. Okay, So these are conflicting constraints, because you need to know the EF to calculate N of T. You need to know N of T to calculate EF, right? It's circular. So how do you get out of this quagmire? How do you get out of this this problem? The idea that people use to get out of this problem is something called a non-degeneracy condition, and we'll talk about it later. Again, we'll come back to this in more detail again, but I'll just brush it up a little bit. Okay. So non-degeneracy condition. Now, the assumption that you have to make to get out of this circularity problem, the problem of needing a EF to calculate electron concentration and needing electron concentration to calculate EF. Okay. To get out of that, you have to assume that the Fermi energy, whatever it is, wherever it is, we don't know where it is. Okay, it is far away from EC, that is the conduction band minimum. Okay, in terms of the temperature. Okay, you need many. Basically, what it says is that at room temperatures, the electrons, if there are electrons at EF, they cannot get into EC. They cannot go to EC. Okay, because you need much more than the room temperature energy to jump from EF to EC, and that's what it says. The same with EV, okay, valence band maximum. Okay, if there is a hole at the top of valence band maximum, it cannot go to EF. It cannot jump to Fermi energy level because it requires a lot more. It would require a lot more thermal energy. Okay, if this condition is met, then we can solve for the electron concentration without this problem, without the EF self-consistency problem. Okay. Now, once we use the assumption actually makes your Fermi Dirac distribution simpler. Okay, because the energies of electrons. Now we are thinking of electrons. Energies of electrons are higher than EC, or at least EC. The EC minus EF is much larger than KBT. Okay, which means this factor is much larger than 1. So what you can do is ignore the 1 and invert that. So this Fermi Dirac distribution function becomes an exponentially decreasing function. All right. So this is more like a Boltzmann distribution function. If you remember Boltzmann distribution function from your school times. Now, once you simplify that, you can now put in the value, put in this form into the equation that I just wrote up here. Okay, this equation up here, you can just plug that into this term. Okay, and evaluate the integral. Okay? With the whole Fermi Dirac function, it is not easy to evaluate the integral. With that simplification, it's much easier to evaluate the integral. Okay? And once you do the integration, this is what you would get. The total electron concentration. Sorry, we have not done the integration yet. So this is your density of states. As I said before, it goes as square root of E. Okay, this comes directly from going from K to E, going from momentum space to energy space in your integration. If you don't remember that, you can brush it up. So this is your density of states, and this is the Fermi Dirac distribution function simplified with a non-degeneracy assumption. Okay. Now you can integrate that. Okay. Once you integrate that, I'm not doing the integration. You don't have to do it either because people have done this before you, and you can just take them as granted and you can trust them. Okay. So your total electron concentration is some factor, a constant factor, times exponential EC minus EF over KBT, a negative EC minus EF. Okay, this constant is called an effective density of states. Okay, it's called an effective density of states function. It's basically density of states. You're basically clubbing all the states available in conduction band and condensing that and putting all those states at EC, exactly at EC. Okay, so that's what is called an effective density of states. Now your states are not spread throughout the conduction band, but they are localized at EC. Okay, So that is the number of states available at EZ, which you can simplify that as a NCT. So NCT is your effective density of states. And you can remember that this is a function of temperature. So as you increase the temperature, the number of available states actually increases. Okay. And that's for this is for electrons. You can do the same calculation for holes. And by the way, you can also write that in CFT, which is this constant. You can write that in a much more dimensionally transparent way here for calculation of the density of states. Okay? Now you can see that the number of density of states available is about 10 to the power 19. So you can actually store about 10 to the power 19 electrons in the conduction band effectively, but usually it's not about that much. Usually it's lesser than that because you have this exponential factor. So that decreases the number of electrons in the conduction band. But effectively, you can store those many electrons. You can store about 10 to the power 19 electrons in the valence band. Sorry, in the conduction band. Okay? And as I wrote about for N0, it's the same thing for P0. Okay? That's the number of holes, the hole density. Now, you have two relationships. One is for N0 and the other one is for P0. Okay, and for N0 you have exponential minus EC minus EF, and for P0 you have minus EF minus EV. Okay, when you multiply N0 and P0, you can see that the EF drops off. Okay, you have a relationship which does not have the Fermi function. Okay, this is what we wanted basically. We wanted the Fermi function to drop off so you can calculate the electron density. Okay, because earlier I said the electron density calculation needs EF. Okay, now you don't need EF. Okay? All you need is EG, the gap, the band gap. This equation is important equation, and you have to remember that. So N0 P0, the electron concentration times the hole concentration in any material, okay, equals the effective density of states in the conduction band times the effective density of states in the valence band times exponential minus EG over kBT. Okay, it's called a law of mass action, and this is applicable even if your material is not intrinsic. Okay? Even if you have doped your semiconductor, this is still applicable. Okay? Now let's apply this for intrinsic case. In intrinsic case, you know that N0 is the same as P0. So the number of electrons, the number of holes are the same because you have not doped the material, and only when a carrier is created, it always creates an electron and hole pair, both at the same time. So you can just say N0 and N0 and P0 as Ni. Yeah, this is the intrinsic electron concentration or hole concentration. So Ni square is this whole thing, and Ni is square root of that. Okay. Now you have the total number of electrons in the conduction band as a function of these parameters, as a function of your effective mass, and as a function of the energy gap and temperature. Okay, without EF appearing in it. And again, you can see that this is a very strongly varying function of the temperature You know, it's an exponentially varying function of temperature. If you increase the temperature, okay, this the exponential function goes smaller and smaller, and the electron concentration shoots up to 10 to the power 19 per centimeter cube. Okay. Now at room temperature, okay, this is I'm sorry, I forgot to write that here. Please. Write that. It's at room temperature T equals 300 Kelvin. This is the density of electrons, observed density of electrons, and you know, people calculate that also. It's of the order of 10 to the power 10 and 10 to the power 6 and all that. It's not 10 to the power 19. Okay, that's the maximum number of electrons that you can have, but you don't usually have that because of the exponential factor. Okay, because the EF is well below EC, meaning the Fermi energy is between EC and EV. So that reduces the factor, reduces quite a bit. Reduces the density of electrons quite a bit. Okay. Now, once you know that, once you know Ni, as I told you, if you have the number of electrons or density of electrons, then you can easily work out EF as well. Okay? So we can, because EF is derived, or EF is, the way you understand EF is by assuming that you're filling in electron over energy levels, filling up the energy levels with electrons until you're exhausted of all the electrons. Okay. So from the equations, from the equation n naught equals p naught, you can just equate n naught and p naught, and because n naught and p naught are the same for intrinsic material, we can equate that and get expression for Fermi energy. Okay? So Fermi energy is half EC plus EV. That is, it's called a mid gap. Basically, it's the energy between EC and EV. Okay, plus kBT ln dB over NC. Okay, that's the effective density of states divided by at the valence band maximum divided by the effective density of states of the conduction band minimum. So you can substitute for PB and NC. I've shown the equation there. MSE constants, and it depends on effective masses. Okay, just got a brain freeze. Okay, so this is your equation for Fermi energy. All right. If you know the effective mass of holes and effective mass of electrons, and you can evaluate where the Fermi energy is with respect to the mid gap, with respect to the middle of the band gap. Now, I think I've told you guys clearly that the effective mass is actually inverse of the curvature of the band diagram, right? So if you look at this diagram, let's say, here the valence band has a very low curvature, okay? Because the effective mass is inverse of the curvature, because the effective mass here, if you the distance between these two is high and positive, which means your Fermi level is going to move towards the conduction band. Okay, so if your effective mass of holes is higher, the Fermi level is going to move towards the conduction band. On the other hand, if it is small, if the curvature is high of the conduction of the valence band, then the effective mass is small, and the EF actually moves down towards the conduction, towards the valence band. The curvature of conduction band does not vary much, even though I've illustrated it like this. The curvature usually doesn't vary for a conduction band as much. Okay. Valence band actually does vary a lot. Okay. 2 more minutes. Any doubts so far? Any questions? Yeah, I hate these kind of classes because it has become complete monologue, and I don't even know if you guys are getting it. Any feedback? I would like to hear some voices from the void.
Sir, can you explain once again the relation between the curvature of the valence band and the shifting of the Fermi energy level?
Okay, thank you. Sure, I will. Okay. Now look at this equation. Okay. This is the distance that the Fermi energy moves from the mid gap. This when I say mid gap, I mean just this EC plus EV over 2. It's exactly in the middle of EC and EV. So if this is positive, it just means that the EF is closer to the valence, closer to the conduction band and away from the valence band. If it is negative, if this is negative, it just means that the Fermi energy has moved towards the valence band. Okay. Now this difference is log of MP star over Mn star. MP star is basically the effective mass of holes divided by effective mass of electrons. Okay. Now effective mass of holes is inversely proportional to the curvature of the valence band. Okay. What is the curvature of the valence band? What is the mathematical expression for the curvature of the valence band? Does anyone remember? curvature of valence band or conduction band, doesn't matter, curvature. What is just mathematical expression for curvature? Doesn't matter about valence band or conduction band. Given a function y equals f of x.
Sir, the double derivative of the function with respect to the x-axis.
Yes, exactly. So because in band diagram you have the energy as the y-axis and k as the x-axis. Okay, k is the momentum, crystal momentum. Now it's del square E over del K square. I don't know how you say it. I said dou. I don't know what you call it. Now dou square E over dou K square, and that is your curvature. Okay, so your effective mass is 1 over that. Okay, so if the curvature is large, it just means that the effective mass is low, right? If you consider a valence band with a high curvature, low curvature, then I will have a large effective mass. Okay, and when my effective mass is large, the factor that goes in here is large, which means this factor is positive. Okay, this is larger than this, which means this whole thing is positive. So EF actually moves towards the conduction band. And if my curvature is small, curvature is large, and my MP is small, the effective mass is small, then this is smaller than this. Okay, my effective mass, whole effective mass is smaller than the electron effective mass, which means that this whole term becomes negative. Okay, and then EF actually goes down to towards the conduction band. Okay. All right. So yeah, no problem. Okay. Now we can kind of graphically understand this product. Okay. This whole electron concentration equals density of states times the Fermi Dirac distribution function. This whole thing can be expressed in a neatly graphical way, a neat graphical way. Okay, so I'll go over that. The density of function, density of states is it goes as square root of energy. It's E minus EB or EC minus E. Okay, depending upon whether it's a valence band or conduction band. That's your density of states. Density of states actually increases with energy, but it increases very slowly as a square root. Okay, it's not even e power 1; it's e power half. Okay, and your Fermi Dirac distribution function actually, once you approximate it using the non-degeneracy condition, it becomes a Boltzmann factor, and the Boltzmann factor decreases with energy exponentially, really fast. Okay, so you have in the electron concentration equation, you have a slowly increasing function of energy times a rapidly decreasing function of energy. So what happens when you multiply an increasing function and a decreasing function? Anyone? Anyone? Anyone?
So an increasing function?
Yeah, a slowly increasing. When you multiply a slowly increasing function by a rapidly decreasing function, what do you get?
So decreasing function? I'm guessing, so I'm not really sure.
Yeah. Okay. Okay. So what happens is it initially increases and then it goes down. Okay. Because both these functions are 0 and equal 0. Okay. And this function increases slowly, whereas this function decreases rapidly. Okay. Now, when you look at this graph, there is a bump. That's what I want. It's a bump, basically. There is some place where you have a non-zero function, and everywhere else it is 0. Okay, that's all there is. So you have a bump, basically. There is a bump right there. So by the way, this whole diagram is kind of messy. Diagram. I'm sorry about that. If you want to have a better version, you can go to Neyman's book. Okay. So here it is inverted. Okay. The y-axis here is the independent variable, energy. Okay. So I am plotting N of E, the electron concentration, as a function of E, but my energy E here is a y-axis, okay? And my x-axis is the function. Okay? It's either G of E or F of E. I'm plotting both of them on the same graph, okay? Now, this is G of E, okay? This is G of E for valence band. And because G of E for valence band is square root of E minus EV, it grows like that, okay? And same for GC of E, G of E for conduction band, okay? Where is my code? So my Fermi-Dirac distribution function, if you see EF, actually the Fermi-Dirac distribution function crosses EF at half, exactly a value of half, and it goes to 1 below EF pretty fast, and it goes to 0 above EF pretty fast. Okay? So you're multiplying these two functions. You're multiplying G of E for valence band times 1 minus F of E, okay? So this is 1 minus F of E. You're multiplying this times that, because 1 minus F of E goes to 0 on this side, because F of E goes to 1. 1 minus F of E goes to 0 pretty fast, and that times this gives you this bump, okay? And this function times this function gives you this bump, okay? Beyond this point, even though this function is non-zero, the Fermi-Dirac distribution function is 0, so this goes to 0. And the same thing here. Beyond this point, much below EV, even though the GE is non-zero, 1 minus F of E is 0. Okay? So that goes to 0 as well. And if you look at the total number of electrons, at each and every point, the height of the curve here represents the total number of electrons at a given energy, okay? When you integrate over all energy, so N of E of T, N of E comma T, when you integrate that, you get N of T, okay? So the whole area under this curve gives you the total number of electrons per unit volume. Same here for holes. Okay. So the total number of electrons here, N naught, is the same as P naught for intrinsic material, so the curves look symmetric. Okay, that's for intrinsic case. Now, if you go for extrinsic case, what you're doing is, in extrinsic case, you're adding material that can either give you electrons or give you holes. Okay, and we'll see how that works. So what you do is basically, well, when you grow the material, you intentionally add impurities to the material. Let's say you take a fourth group material. Fourth group is silicon, germanium, and all that, which has 4 electrons on the valence shell. Okay, so it can form 4 bonds with the neighbors. So silicon forms 4 bonds with the neighbors. Now, if you add, let's say, phosphorus. Phosphorus is a 5th group element, okay, and it has 5 valence electrons. Now, because it is located inside a silicon, whereas the number of bonds with each atom inside silicon is 4. So silicon forms 4 bonds with its neighbors, and so when you make a phosphorus sit inside a silicon's lattice, phosphorus only can form 4 bonds with its neighbors because its neighbors are all silicon. So phosphorus has 1 electron hanging out free. Okay, so it can actually diffuse out from the ion. Phosphorus atom, when it loses an electron, it becomes an ion. It can move around the phosphorus ion. Okay. Now, can it entirely leave the ion? Can somebody answer that? Can the electron offered by phosphorus, can it completely leave? No. Okay. Why do you think so? Why do you think so?
So because it will be bound to the nucleus, the positive nucleus of the phosphorus atom.
Perfect. Yes, perfect. So that's the reason. It is not going to move very far, because when it moves, the phosphorus gains a positive charge, and that positive charge binds that electron, right? Okay, now you can think of this whole situation as a hydrogen atom. Right, in the hydrogen atom, you have a nucleus, you have a proton, and the electron goes around the proton because of the electrostatic attraction. The same thing happens here. But what is different? What is different is that the whole thing happens inside another material. What that does is that it reduces the electric field intensity. substantially. Basically, the permittivity of the substance dictates how effective the electric field is, connecting the positive ion, phosphorus ion, and the electron that has just gotten loose from it. Okay? So if the permittivity is high, what that means is that the electron is not quite tightly bound to the phosphorus ion. Okay, it can roam around freely to a certain extent. So the radius of the electron is larger compared to the hydrogen atom. It is the same situation as the hydrogen atom. Okay, it's exactly the same as hydrogen atom, at least mathematically, in a simplistic fashion. But the electron is not as tightly bound to the nucleus. Okay? It kind of roams around freely, but not too far. So what happens is, let's say for hydrogen atom, if you want to release the electron completely, if you want to make the electron free, basically ionize the hydrogen atom, how much energy do you need? Anyone? It's a constant that you all need to know. Okay, and that value is 13.6 electron volts. Okay, that's a constant that you need to know. Okay, it's the binding energy of electron to the hydrogen atom is 13.6 electron volt. So that is the amount that you need to give to the electron to for it to leave the proton. Okay, so what is the binding energy of electron with the phosphorus? That is of the order of milli-electron volt, not electron volt. So it's about 1,000 times smaller. Okay, so you don't need so much energy to release the electron from the arms of phosphorus, if I may say so. Okay, so the energy that is needed to ionize the phosphorus impurity is quite low. Okay. Okay, I'll get back to that later. Now, if you want to add holes, you add a trivalent material like boron. Okay, did I say boron or moron? Boron. Nice. Sleepy. Okay, so the boron has 3 electrons in the valence band, and it can take one more electron to form bond with silicon. So basically, it uses a hole, and because it attracted an electron to form the valence band, it has gained a negative charge, which means the hole is bound to the negative charge of boron. Okay, so you have the same situation as I said before, but now it's the nucleus is negative, and the electron basically is the hole is a positive charge. Okay, that's all there is. Now you can look at the band diagram. Okay, so the energy that the energy levels of the donors, or sorry, here the acceptors, the energy levels of acceptors is pretty close to the valence band maximum. Okay, what that means is that it is a lot easier to release the hole from the boron and make it conduct. Okay, basically it's a lot easier to release the hole and make it roam through the crystal. When you do that, you're basically pushing the hole from the acceptors level to the valence band level. So the hole actually falls down. Okay, and the electrons actually jump from the valence band to the acceptor level. Okay, so it makes more holes available at the valence band. It's a lot easier to visualize the donor levels. Okay, donor levels. So there are electrons bound to the phosphorus. Okay, and that energy is drawn by a line here. Okay, that is ED. And when you supply a little bit of energy, as I said, it's 25 milli-electron volt. It's not much. So when you apply that much of an energy, but just by temperature, the electrons bound to the phosphorus, they go into the meat of the semiconductor, go into the conduction band. So you're ionizing your. Oh, I'm shooting over time. Is that a problem? Do you guys have a class? Anyone?
Yes, sir, we have a class.
You do have a class? Okay, I have short overtime. Okay, I will leave it right here then. Okay. All right. Then I'll see you maybe next week or on Wednesday, depending upon how available. Okay. See you all. Bye for now.